So now we've got a region bounded by these equations. So y equals 2 minus x over 2, y equals 0, y equals 1, x equals 0. And we're going to revolve it about a few different axes. I wanted to wait and graph it with you in the video so we could talk through this part of it. I'll go with these equations first. So y equals 0 is the x-axis. So that's here. Y equals 1, so that's a horizontal line. So many markers. Horizontal line here. So there's y equals 1. X equals 0, so that is the y-axis here. Okay, and then our fourth boundary equation, y equals 2 minus x over 2. So this is a linear function because you've got x to the first and y to the first. I might graph it by plotting points, maybe. So if I consider certain x values, so if x equals 0, then y would be 2 in that equation. I'm going to put some of these down. Oh no. Okay. If x equals 0, y equals 2 up here. If x equals 1, well, I don't really want to mess with that. If x equals 2, then I have 2 minus 1, right? 2 minus 2 over 2. So I'll have 1. So that's actually going to be a point of intersection right here. And if x equals 4, then I have 4 over 2 here, which is 2. So 2 minus 2. When x equals 4, y will be 0. And the slope here is negative 1/2. I mean, you could also use slope-intercept on this one. The y-intercept is positive 2. The slope is negative 1/2, so it goes down 1 over 2. So that would be fair also. So keeping in mind that the other boundaries are the x-axis, or sorry, the y-axis, the x-axis here, and then this blue line, then the portion of this line that we really care about is this part right here. Right, that's going to be what closes out this region. And so the region being enclosed in this case is this kind of wedge shape here. Now it's going to be revolved first about the y-axis. So one important thing to note, at this point we have the disk method and the washer method. In both of those methods, it's important that the rectangle is perpendicular to the axis of revolution. So in this case, our rectangle would have to be lying horizontal, like this. This is our typical rectangle. That way, if you can imagine, when you revolve this, you're going to get a disc shape. So in part A, when it's revolved about the y-axis, we're going to be using the disc method. The other reason that, or motivation here for drawing my rectangle horizontally is if you drew, so let me sketch the region real quick over here. If we used a vertical rectangle to represent our slice of this region, then the height of the rectangle would be 1 as x ranges from 0 to 2. And then as x ranges from 2 to 4, the height of the rectangle would be determined by this y equals 2 minus x over 2 function. And so when you have the height of the rectangle determined by different functions at different values, that's something we want to avoid. So this region is what we call horizontally simple. When you look at it right to left, it's simple. It's always got the blue boundary on the right. It's always got the y-axis as a boundary on the left. It's not vertically simple, because when you try to look at your rectangle vertically, you've got different boundaries for different values of x. So we say this is an example of a region that is not what we call vertically simple. So we do not want to use a vertical rectangle for that reason, but it is horizontally simple. If we draw a rectangle lying horizontal like this, the boundaries are consistent. Red always on the right, black always on the left there. Horizontally simple. So we definitely want to use a horizontal rectangle as our typical rectangle to slice this region. So get rid of this. The rectangle, again, is perpendicular to the axis of revolution. There's no empty space between the region and the axis where it's being revolved. It's not going to leave any empty space, so it's not going to leave a hole. So that's how we know it's disk as opposed to washer method. Okay, so formula when you use disk method. Volume equals pi times the integral from a to b of the radius. I don't know, we could use capital R or lowercase r. I just used lowercase r squared. Oops, and I wrote dx, but this is something you need to be careful of. It's not actually dx. When you use a horizontal rectangle, the width of our rectangle is dy. Whenever you draw your rectangle standing up like this, your tiny width is dx. It's an increment of x. When you draw your rectangle horizontally, your tiny width of the rectangle is dy. It's an increment of y. If you imagine that whole partition deal, we'd be taking the partition along the y-axis, not the x-axis. So this needs to be in terms of y. That's important. Okay, now the radius. What's the radius of this disk? So if you revolve that rectangle and form a disk, my sloppy disk there, the radius of that disk would be this distance right here, right? This is the radius. So that's the difference between, if it's a horizontal distance, then it's the difference between x values. So it's the difference between, we have to get rid of that dy's in my way. Along this boundary, well, it's coming from this equation, but what we really need is, we need that equation solved for x, because I need to know what's this x value here and what's this x value here. And then the difference between those x values will be the radius. So over here, x is 0. That's pretty straightforward. That's exactly where this boundary came from. Over here, I don't know if you guys can hear the plane in the background. It's this boundary, maybe I'll write it in red, is coming from this equation, y equals 2 minus x over 2, but we want it expressed as in terms of y. We want to express it the one specific x value written in terms of y, because we're going to integrate in terms of y. So I guess maybe let's subtract 2 from both sides. So y minus 2 equals negative x over 2. And then multiply both sides by negative 2 times negative 2 times negative 2, which will give me just positive x on this side. If I distribute the negative 2, I'll have positive 4 minus 2y. I always like it better to write the positive term in front. So x equals 4 minus 2y when we take that equation and solve it for x. And so the radius, like I said, is the difference between those x values. So the radius here, you do right minus left. So 4 minus 2y minus 0. So the radius that needs to go in the formula right here is 4 minus 2y. And that's the radius squared. This minus 0 is going to have to go. It's not doing anything anyway. So the volume is pi times this integral. We need limits of integration. If this is in terms of y, then your limits of integration should be y values. So this is as y goes from 0 to 1. Remember that this upper boundary right here, this blue line, if you can still see it, was from this boundary equation. So this would be as y goes from 0 to 1. And this is where you can stop in the homework and on exams. So that's the answer to A, if this thing is revolved about the y-axis. So now I want to look at what if it's revolved about the line x equals 5. So I'm going to have to get rid of this. I'm going to write the answer right here real quick. 0 to 1, 4 minus 2y squared. Okay. Whoops. Okay. So, sorry. Now let's suppose it's revolved about the line x equals 5. So quick illustration here. So this is as y goes from 0 to 1. This may not be completely to scale this time. So remember our region looked like this. It was straight until we got to where x is 2. And then we were going along this. Actually, I'm going to write this boundary in red. Which the equation for this boundary we expressed in terms of y, so it was x equals 4 minus 2y. We've got the rectangle laying horizontally like this because this is a horizontally simple region. If we try to set up vertically, the boundaries change, so we want to avoid that. Now it's revolved about the line x equals 5, which is over here. So still, the rectangle is perpendicular to the axis of revolution. So this is still disk or washer method. Since there's empty space between the axis of revolution and the rectangle, this is going to be washer method for part B. We're working on part B now. Formula for washer method is pi integral from a to b of the outer radius squared, which I like to use big R, minus the inner radius squared, which I like to use little r for that. I know the book uses different notation. And the variable of integration, whenever you use a horizontal rectangle, variable of integration is y. This is dy. So it's still going to be in terms of y. Limits of integration are still going to be lowest y to highest y, corresponding to this region. So 0 to 1. So the only thing we have to fill in is the expressions for the outer radius and the inner radius. So we'll do outer radius first. The outer radius here is the distance from the axis of revolution to the outer boundary. Which, when I say outer boundary, that's relative to where you're revolving it. So if I'm revolving it about this line over here, then the outer boundary of the region is the one way over here, which was x equals 0. And while I'm at it, well, no, never mind. So outer boundary is x equals 0. We're revolving it about the line x equals 5. So the difference between those values, this distance right here is your outer radius, your big R, and then just do right minus left. It's a constant outer radius of 5. When you've got a flat outer edge like this, you will get a constant for your radius. So in this case, 5 squared for the outer radius. Okay, now inner radius. I'm going to get rid of this, I think, because it makes it harder to see. So for inner radius, we need to look at, so what's the inner boundary of the region? So relative to this axis of revolution, the inner boundary is this. Another way to reason that being the inner boundary, if you picture this thing actually being revolved, I'll try to do a quick sketch down here, but so when you revolve this, if you can kind of picture the shape that you get, the inner boundary will be this diagonal boundary here, the inner boundary of that three-dimensional solid. So the inner boundary is this x equals 4 minus 2y boundary. And the radius, get rid of this dy, is the distance between those. This is your inner radius, your little r. So again, do right minus left. So this is 5 on the right minus 4 minus 2y on the left. And you could distribute, well, nah, you'd have to, oops, I'm sorry, don't square it yet. So you could distribute the negative and combine like terms if you want. I'm going to leave it the way it is. You're not obligated to do any simplifying on these. So this is 5, I'd have outer radius minus, or sorry, outer radius squared minus inner radius, which is 5 minus 4 minus 2y. All squared. Sorry, that's pretty smushed. But so inner radius is 5 minus 4 minus 2y, which maybe I should have combined like terms in retrospect. So that'd be 5 minus 4, which is 1, and then distribute the negative plus 2y. So this is 1 plus 2y, just in the interest of space and having this be readable. I'm going to write it that way. 1 plus 2y all squared dy. And so this right here is your answer to part B using the washer method. Okay, so one last one. I know this video is getting a little long, but if it's revolved about x equals -3, I'm going to do one more. So pause it now if you want to see what's on the screen now. So I'm redrawing this region one more time. Oh, yikes. Okay. So now we're revolving it about the line x equals -3, which let's say is back here. And again, I mean, you want to draw your typical rectangle that you can refer to when you're setting this up. So here again, the rectangle is perpendicular to the axis of revolution, and it leaves an empty space between the actual axis and your rectangle. So this is going to be washer method again. Formula for washer method is integral, forgot the pi out front. The pi couldn't go inside or outside the integral. I like to write it outside. As y goes from 0 to 1 again, because this is going to be an integral in terms of y, because it's a horizontal rectangle. So integral as y goes from 0 to 1 of outer radius squared minus inner radius squared integrated with respect to y. So that's the plan. So we need to find the outer radius and the inner radius. Outer radius. So relative to this axis of revolution, let me switch colors here. Relative to this axis of revolution, the outer boundary will be the farther one away, which is this one. So now the outer boundary, this is different from that last example. Now the outer boundary is the x equals 4 minus 2y boundary. And the distance between the axis of revolution, which is x equals -3, and the outer boundary, so this distance here, you do right minus left. So big R is 4 minus 2y minus left, -3. So actually plus 3. And that makes sense. We're adding 3 units of space, where in the first problem, your radius was just 4 minus 2y. Now it's 4 minus 2y plus 3. So we're adding 3 units to the radius here. I'm going to go ahead and add that on. So that's going to be a plus 3, so this will be 7 minus 2y. So the outer radius in this formula should be 7 minus 2y squared. We've got the pi out front, integral from 0 to 1. Now we just need the inner radius, and we're done. So inner radius is the distance from the axis of revolution to the inner boundary. So the boundary that's closest, boundary for this region that's closest to the axis of revolution is this one, which is x equals 0. And so the inner radius is this distance here. If you do right minus left, or you could just look at it and see the distance, but if you do right minus left, just for consistency, it's 0 minus -3. 0 minus -3. So 3. And it's fair to say, I'll just look at that and say it's 3. Sure, that's reasonable. So inner radius is 3, and then we square it as part of the formula, the old pi r squared times the height, which is the volume of the cylinder, where the height is dy. So again, this is where you would stop. At this point, you've set up an integral that gives you the volume of this solid of revolution. Just by the way, so if you wanted to actually find the volume, you would have to multiply this out. So square the 7 minus 2y, subtract 9, combine like terms, and then it's just going to be power rule for integrating. So thanks for making it to minute 20 of this video.